So our WSN project is on the topic forest fire detector. So our agenda is, for example, there is a forest near Chennai which is prone to wildfires, especially in dry seasons. So the watchtowers and manual patrols are not continuous or efficient for larger areas. So we need a solution for this. Our goal is to continuous 24/7 environmental monitoring using a network of smart sensors. How it works: sensor placed across the forest, each node checks the temperature and humidity. Then it detects the sudden rise in temperature and drops in humidity signal fires. Then it alerts through the node and it identifies the fire location.
I'll be covering the problems faced at the local level. Let me start by explaining why early fire detection matters in our context. We'll be taking an example of the Nanmangalam Reserve Forest. It's a key green lung of Chennai, but it's highly vulnerable to forest fires during dry seasons. Traditional methods have major limitations. Watchtowers only cover a limited area, and manual patrols are resource intensive and simply can't monitor 24 by 7. So there is a strong need for an automated real-time and scalable detection system. A small fire, if not detected immediately, can escalate into a catastrophe within minutes. To solve this issue, we have proposed a wireless sensor network for autonomous 24 by 7 environmental monitoring. It works as we deploy a grid of low-power sensor nodes throughout the forest. Each node continuously monitors ambient temperature and humidity. If any node detects a sudden spike in temperature and drop in humidity, which are classic signs of fire, it triggers an alert. A high priority alert packet is sent through the network to a central base station, which pinpoints the fire's origin instantly. Next, we'll be diving into the system architecture of our project. Our system architecture includes four key layers that work together, transmit, and analyze data. Layer 1 is the sensor node, which includes components like microcontroller 8266, MQ6 gas sensor, and a DHT11 sensor deployed in the forest to collect real-time temperature and humidity. Layer 2 includes WSN communication. Using the 802.15.4 radio and RPL routing protocol to relay data efficiently, we manage the whole process. Layer 3 includes the gateway or sync node. In this, we create a central hub as a range station. It collects all the data and bridges into our application. Layer 4 is the host application. We have currently used Thingsboard to deploy and visualize whole incoming data and the trends. This helps in monitoring and determining all the issues, formal alerts, and everything, and send it to the authorities. This layered approach ensures continuous monitoring, rapid alerting, and seamless integration with authorities for effective response. Next, I'll be asking Rishi to explain the flowchart of our project.
This slide shows the implementation flowchart for our forest fire detection system, which outlines the project's core logic. The process begins at the start block. From here, the system enters its main operational state. The sensor nodes in the field continuously monitor the environment. At every new reading, the system makes a critical decision. It checks for an abnormality, that is, if the temperature or smoke level has crossed our preset fire warning threshold. If the conditions are normal, the system simply continues to monitor. However, if an abnormality is detected, the system immediately performs two actions. First, it relays the dangerous data to the central gateway, which then updates our dashboard to visually display the high temperature alert. At the exact same time, the system also transmits a separate alert, which could be an email or SMS notification to the authorities. This transmitted alert is also logged on the dashboard, confirming that the notification was successfully sent. This dual path process ensures that we not only get an immediate visual of the data but also an actionable high priority alert for a rapid response. This slide details the hardware connections for our sensor node. The brain of our operation is Node MCU ESP8266, which is powerful microcontroller with built-in Wi-Fi. The DHT sensor is powered by the 3.3 volt pin, and its data line is connected to digital pin D4 in the Node MCU. The MQ6 smoke sensor requires 5 volts for its heater, so its VCC is connected to the V-in pin in the Node MCU. Its analog output A0 is connected to the ESP's A0 pin, which allows us to measure the level of smoke in the air.
Microcontroller code. This slide shows the implementation code running on the ESP8266 microcontroller. The DHT11 sensor records temperature and humidity, while the MQ6 gas sensor detects smoke or gas concentration. The microcontroller connects to Wi-Fi and uploads the data to ThinkSpeak for real-time monitoring. If the MQ6 value exceeds a certain threshold, the system detects it as a fire and triggers an alert. This ensures continuous and automated environmental sensing. Serial monitor output. Here we can see the live data output on the serial monitor, showing temperature, humidity, and gas levels in a real time. Whenever a significant gas value is detected, the message gas detected appears. This helps us to verify that our sensor and ThinkSpeak communication are functioning properly, confirming that the system is successfully capturing and transmitting data. Future plans and conclusion. For future improvements, we plan to integrate flame and smoke sensor to improve the detection accuracy. Use LoRa or satellite communication for longer range and AI-based edge detection for faster responses. We also plan drone integration for real-time visuals, GPS for precise fire mapping, and solar energy to make the system sustainable. In conclusion, VanGuard demonstrates how wireless sensor networks can provide an intelligent real-time solution for early forest fire detection, protecting your forest in a smart and scalable way.